Okay, this is sample problem 14.7. Now we're going to look at second order kinetics. In this problem it says that iodine atoms combine to form molecular iodine in the gas phase. I gas plus I gas forms I2 gas. So these two atoms are colliding with each other to form a molecule. The reaction is second order. The equation can also be written as 2I gas converted into I2 gas. The rate constant is 7.0 times 10 to the ninth, reciprocal molar, reciprocal seconds at 23 degrees Celsius. If the initial concentration of iodine, I, that's atomic iodine, is 0.086 molar, calculate the concentration after 2.0 minutes. Calculate the half-life of the reaction when the initial concentration of iodine is 0.60 molar and the initial concentration of iodine is 0.42 molar. I've written the two equations that we need to use here for A and B. They are from table 14.5, so you might want to take a look at that table and write those formulas down, because the table includes not just second order, but it also includes first order. It also includes zero order. So you need to use the right equation for the type of order that you're looking at. So if the problem says second order, you want to use these two. Okay? So let's take a look at the first one. What we're given is the value of K, so we know K. We're also told that we want to find the concentration of A after 2 minutes, so we also know time, T. And we're also given that the initial concentration is 0.086 molar. So those values are all given, so we just need to solve for A. Again, it's useful just to use A or B instead of actually writing out the entire chemical formula. Some authors will put the entire chemical formula, and that's fine. You can do that as well. So I'm going to go ahead and just put everything in. 1 over the concentration of A. A is the iodine we're looking for, is equal to K. Now, this value of K is gigantic. It's a really large value of K, which means that this reaction is fast. The larger the value of K, the faster the reaction is. The amount of time is 2 minutes, but we want to have it in seconds, so that's 120 seconds. Okay, right? Why do I want it in seconds? Because the rate constant is in reciprocal seconds there, so we're going to have it same units. So that's minus kT plus 1 divided, just be careful, right? It's 1 divided by the initial concentration. Okay, so you get kind of funky units here. 1 over concentration is molarity minus 1. Okay. So let's go ahead and do the calculation. 7.0 times 10 to the 9 times 120 is going to give you a massive number, 8.4 times 10 to the 11. The seconds are going to cancel, so you have molarity to the minus 1. And then 1 over 0.08, I guess I'll just go ahead and calculate that. This second term is so small compared to the first one. Like 1 divided by 0.086 is 11.6. Molarity minus 1, right? 1 over molarity. So if you were looking at this in dollars, this would be the equivalent of $840 billion for the first term, and then $11.60 for the second term, right? So I guarantee anybody that has $840 billion, you know, $11.60 is pretty small. It's not going to really affect their net worth. And the same is true for this one. That second term is so small it will not show up in the answer. So I'm just going to write, 1 over concentration. You can try it in your calculator. You can add those two and see what you get. But you're going to get 8.4 times 10 to the 11, because that second term is just so small compared to the first one. Now that's 1 over A. So how do we find A? We just take the reciprocal, 1 divided by that. So 1 over 8.4 times 10 to the 11. And now you get this really, 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 really small number. Okay, so A would be 1 over 8.4 times 10 to the 11. And so I get 1.2 times 10 to the minus 12. Again, 1 over 1 over. You have molarity of the minus 1 in the denominator, so you're going to get molarity. That's practically 0. Now, technically it's not 0, but it's really, really small. It's a very low concentration. If you think about it, we started off with 0.086 molar. We're down to 0.11 zeros and then a 1. So it's really, really small concentration. Okay, and that's because the rate constant is large. The larger the rate constant is, the faster the reaction goes. So this reaction is just decayed away to the point where there's a very small amount of iodine left over. Now we're going to do the half-life calculation. The half-life, we want to find it out what it is if the iodine concentration is 0.60 molar and the initial concentration is 0.42 molar, okay? Okay. It's actually 2 separate calculations. I was looking at that and I noticed there's 2 separate calculations. So let's try it for the first one. 1 over k. Again, we're going to use the same value of k. Funky units, right? 1 over k. And then we're going to try it when it's 0.60 molar. That's the initial concentration. Those molarity units are going to get canceled. You're going to have 1 over seconds, which is just seconds. So 1 divided by 7 times 10 to the 9 divided by 0.6, and you get a half-life of 2.4 times 10 to the minus 10 seconds. Okay? Now, looking back at earlier problems from first-order kinetics, the meaning of the half-life is how much time it takes for the concentration to go down to half of what it originally was. So in other words, if we start off with 0.60 molar, half of that is 0.30, right? So the concentration will go down to 0.3 molar after this amount of time. How much time is that? That's 240 picoseconds, or 0.240 nanoseconds. That's not a lot of time. That's probably about the amount of time that a really super fast processor does one simple movement of digits in a supercomputer, or in a really fast computer in any case. So that's really, really fast. Notice that unlike first-order kinetics, the half-life actually depends on what the concentration is. It's in the formula right here. It's not for for first order. For first order, the half-life is just 0.693 over k. So you don't need to know, over k. You don't need to know what the concentration was. So now let's try the second one. They just changed it to a slightly different concentration, 0.42. So 7.0 times 10 to the 9th, molarity minus 1, second minus 1, and then we're going to do 0.42 molar. It's not going to change it that much because the dominant feature in that formula is k for this problem because it's so large. 7 times 10 to the 9 times 0.42. We're going to take the reciprocal of that. So you get 3.4 times 10 to the minus 10 seconds. Again, it's a really, really small amount of time. It's going to go down to half its initial concentration very rapidly. So, our initial concentration would be 0.42. After this amount of time, it would go down to 0.21. Okay? Half the initial concentration in that period of time. That's second order kinetics. Again, table 14.5 has all the formulas that you need for these sorts of calculations for first order and second order.